Welcome back, Cat 5 class. In Chapter 15, we're going to cover threads and fasteners. There will be no AutoCAD in this chapter. Chapter 16, the next chapter, will cover threads using AutoCAD. Next slide. How we call out our threads depends on what standard we're using. Also, these standards set up the tolerances on how to create threads on bolts and nuts. Okay, so we have the ANSI standards, ASME, ISO, and we also have the Japanese standards. Okay, so threads, if it's on a bolt, you refer to them as external threads. If it's in a nut or a block with a tapped hole, then you refer to them as internal threads. Okay, so here's an example of external threads, as you can see on a bolt or on a screw. External heads, and at the end we have a chamfer. Notice how it's cut at a 45-degree angle, and that's just to make it easier to attach or to engage with the tapped hole. Sometimes when you're trying to insert a bolt under the hood of a car and it's hard to see the hole, this little chamfer will allow you to at least give you some guidance as you're trying to engage the threads on a engine block, for example, or a nut. Okay, so how do we create threads on a shaft? So this starts off as a solid shaft, and you have to create the threads. One way is to set this on a lathe. So the lathe rotates the screw, and then you come in with the cutter, and it'll create the helix thread. Just look up threads and lathe on a YouTube video. It'll show you how threads are created. So another way of creating a thread is by using a die like the one shown here. So again, imagine this is a solid smooth shaft, and you attach the tool at the end and you turn it. You do need a little pin that goes in here to be able to turn it, and you're going to use an oily fluid, pour it on there as you turn to create the threads, and you do it slowly so you don't break the die. And let's say you wanted to create the threads inside of a nut. This is the tool you would use. You would insert this tool inside of the smooth hole, smooth surface, and you would turn it. So here's the handle for turning, and you would apply once again an oily fluid as you're tapping the hole to create the threads. Same thing if you drill holes in an aluminum block, for example. First you drill the holes. Obviously you're going to drill a smaller diameter hole. Then you come in with these manually, or you can do it on a 3-axis machine where it'll come in with this tap tool, and it'll slowly turn to create the threads. You don't want to go too fast, or you can end up breaking this tool. Okay, let's learn some terms here for threads. So we have the axis of the shaft. We have the pitch, which is the distance from tooth to tooth. And we have the crest, the top of the tooth, and we have the root, the bottom, and the thread depth from the crest down to the root. Okay, here we have the major diameter, which is distance from crest to crest. That's the major diameter. Minor diameter is from root to root. And the pitch diameter, it's not exactly in the middle or the average. It's where this line equals this line. So the distance from the tooth itself, with the depth of the tooth here, and this length here equals each other. And you go to the opposite, and that'll give us our pitch diameter. The one that it's important is the major diameter. Okay, and then we have the angle and the sidewall. Most bolts and nuts will have right-handed threads. That means that you will have to turn clockwise to tighten them. You will also encounter left-handed threads. In this case, you will turn counterclockwise to tighten them. Once again, most bolts and nuts will be right-handed. A few occasions where you will encounter left-handed threads is where you don't want something to loosen up depending on rotation. So one good example is bike pedals. So bicycle pedals, one of them will come with right-handed threads, the other one with left-handed threads, and you cannot mix them. They can only go either on one. One can go on the right side, the other one on the left side. So the reason is so that when you're pedaling, you don't want the threads to loosen up, so it'll go in the opposite direction of the pedaling. Same thing with side mirrors on a motorcycle. Motorcycles, they may end up tapping a car, or as they lean a motorcycle, their side mirror may hit something, and you don't want it to rotate and loosen up, so it'll rotate it in a direction where it actually tightens up. So that's the reason side mirrors on motorcycles do not have the same type of threads. One will be right-handed thread, the other one will be left-handed thread. Now for this chapter, we're going to mostly be working with unified screw threads. Okay, so your typical threads that you see on a machine shop or on an engine block will be unified screw threads. There's also iso threads, very similar as you can see. And there's square threads. We're not going to deal with it in this class, but square threads. And this is ideal for power transmission. So you'll see square threads on a rod or a shaft. Again, we're not dealing with these type of threads, but we also have Acme threads. And this is stronger than the square threads. And for lifting, like jacks, we want to use the buttress threads, are a lot stronger. Okay, so how do we draw screw threads on a drawing? There are three methods of representing screw threads on a drawing. There's the detailed, the schematic, and simplified. Screw thread representation presented in this chapter is in accordance with the ASME Y14.6 2001 standard. So here's an example, the first example, which is detailed threads, where you manually draw one line at a time, not only for a external thread, but also for an internal thread. Now this is time consuming, so typically we don't draw detailed drawings, or I should say detailed threads on drawings. It eats up too much time, and your boss is going to be paying you by the hour. The only time I've drawn threads one at a time is in the classroom. I've never had to do it out in the real world. A simplified version of the detailed threads is to do a schematic thread. So instead of doing the threads at an angle as they really are in true life, we'll just get away with it by doing simple vertical lines to represent threads. So that's one option of how to call out threads. So on the previous slide, we did external threads, schematic threads. This is for internal threads, again schematic. Instead of doing the angled lines like in real life, we just draw simple vertical lines to represent threads, just to speed it up and to simplify it. And finally, the third option of how to draw threads on a drawing is the simplified version, where you don't draw all the threads, you just draw dashed lines indicating where the thread starts. So the threads start here and they end here, and the rest of it is a solid shaft. So that's the simplified version of creating external threads. And the very simplified version of creating internal threads, it's by drawing double dash lines. So instead of having to draw those diagonal lines, you just draw double dash lines indicating threads. From this view, again, we have a block with a tapped hole, as you can see. You would draw a solid object line or circle for the minor diameter, and a dashed line for the major diameter, and that would represent the crest and the root of the threads. Okay, so let's take a look at an example again of threads. This is the simplified version. Another more even simplified version, and it's to save time, is to just not even draw anything to indicate threads. You just point to the cylinder. Typically you draw a thin line to show where it ends. And this is the way of calling out threads. So this call out here that we see with the leader pointing to it, it's telling us, hey, this shaft in this area is threaded. And this is the way you call out threads. So let's go over each part of this note. Okay, so let's go over a note of how we call out a threaded hole or an external thread on a bolt. In this case, we're dealing with an internal thread. Okay, so here we have the leader, and it first calls out the major diameter. So the first number will tell us the major diameter of the thread. We don't call out minor diameter or pitch diameter. We will always call out the major diameter. Okay, and then the next number, so we have dash, and this is 24. So this tells us how many threads per inch. So if this block was an inch in depth, the hole was also 1 inch in depth, then we would have 24 threads. This block was 2 inches in depth, go 2 times 24, and we would have 48 threads going through that hole, that tapped hole. Okay, now UNF. So UNF, U stands for United, N for National, and F for fine thread. So this is the standard we're following, and these are American standards. And there's also a UNC, C for coarse thread, where the threads are further apart, which are more common than fine thread. Okay, now let's look at thread class. So we have a class of 1, 2, and 3, 3 being the best with tighter tolerances, more accuracy. And the type of thread, is it external or internal? External on a shaft, and that would be A, and internal would be B. So this is an internal thread inside of a block. And finally, we have to state what direction the thread's going, right-handed or left-handed. So right-handed is more common. In this case, we're going with left-handed threads. And finally, we have the depth of the thread. So here it's telling us the thread has a depth of 1/2 inch. Okay, there's 3 main types of threads. The Unified National Standards will give us coarse thread, United National Coarse Thread, the UNC. So this is what you commonly see in machine shops, metal forming shops, hardware stores. So coarse thread just tells us that the threads are far apart. Then we have UNF, United National Fine Thread. The threads are tighter together. So in some situations where you have a lot of stress, a lot of forces applied to your bolts or to the holes or the threaded nuts, then we want to use fine thread, especially we have like high RPMs. One good example are the wheel studs. So if you ever change a wheel, a tire on your car, you have to remove the rim. There you're dealing with UNF threads. Fine threads, they're tighter, closer together than coarse threads. Also inside of a combustible engine, where you have rapid movement inside, the parts inside with threads will have fine threads, tighter together. Now things like water pumps, where you attach it to the engine block or where you attach the alternator to a bracket, those will have coarse threads where there's no rapid movement, again like high RPM, like on the wheel studs. Then you'll just use a coarse thread. And then we have extra fine. So one area where you do see extra fine thread is in aerospace, in small aircraft, for example, made out of aluminum, or older passenger planes made out of aluminum. They use fine thread, but in areas where they're using very thin sheet metal. So thin sheet metal where you need to drill holes and you need screws to engage, so you need to throw in as many threads as you can, and the only way is by using extra fine, tight threads together. So here the pitch, the distance between the threads, is very small. So this is for sheet metal with holes. And we also mentioned the thread class. That's the quality of the threads. So we have one which is generous tolerance for rapid assembly and disassembly. And we have class 2 for normal production. And then we have 3, which is high accuracy. So bolts that you see in machine shops, in automotive, in aerospace, they typically use the class 3. You will rarely use 1 or 2 unless you're doing stuff around the house and you're going to your local hardware store. Yeah, they may be a lower class. And if you see the label of A, that just means it's external threads, threads on a shaft, like a screw. And B is for internal threads. Example is threads in a nut or a tapped hole in a block, like an aluminum block, for example. And then we have RH for right-handed threads and LH for left-handed. Once again, RH is the most common. Over 90% of the time, you'll use right-handed threads, maybe even closer to 99%. And since right-handed threads are assumed, typically we won't even call out right-handed threads. It's just assumed it's right-handed. If it happens to be left-handed, then we will use the LH callout. And as mentioned before, there's some things that you can drop off of the note. You can drop off the class. Again, there's class 1, 2, 3. You don't have to list it. You don't have to list if it's external or internal. It'll be obvious from the drawing. And again, most threads are right-handed, so you don't call out the RH. The only time you do call out the type of thread is when it's an LH, a left-handed thread. Okay, so we're going to be looking at inches. And on the next chapter, we'll be looking at millimeters. So for now, we're going to focus on inches when it comes to threads. Okay, so here's a note for a thread. So the quarter, what does the quarter tell us? So the quarter will tell us that we're dealing with a major diameter of 0.25, so it's just 1 divided by 4, 0.25 inch major diameter. The dash 20 tells us that there's 20 threads per inch. Okay, so if the thread is 1 inch in length, it'll have 20 threads. If it's 2 inches in length, it'll be 2 times 20, it'll be 40 threads. If the length is only ½ inch, then we'll just cut this in half. We'll have 10 threads. Now, what is the distance between the threads? That's the pitch. All you have to do is take 1 divided by 20. There's 20 threads per inch. So that tells us that if you take the inverse, 1 over 20, the threads are 0.05 inches apart. And now we have UNC, that's coarse thread. Okay, so United National Coarse Thread. The 2 will tell us the class. And again, the most common one you will use is the max, which is 3. And 2 is for normal, 3 is for high end. That means the tolerances are tighter. Okay, and then the A tells us that we're dealing with external threads, threads on a bolt, threads on a shaft. And finally, the RH tells us we're dealing with right-handed threads. Okay, in the back of your book, in the index area, there's this table. And this table is 4 threads involving inches. I don't have the entire table here. There's some rows missing with larger diameters. Okay, so let's take a look at ½ inch. So when you see if your boss tells you to order ½ inch threads, they're referring to 1/2 is equal to 0.50 inches, and that's your major diameter for the threads. If we order quarter, 1/4, that's 0.25 inches for your major diameter. And anything below 0.25, forget what the formula is used, but they use a formula now. If your boss asks you to order number 10s, it involves like something like 10/64 plus some fraction, and it'll come up with this number. Same thing with these others. So there's a formula used to come up with these numbers and give you these diameters, which is not important. We can just always use the table here. Okay, so if your boss asks you to order number 10, a number 10 bolt, which has a diameter of 0.1900, major diameter, you want to know, does your boss want coarse thread? So that's 10-24, so 24 threads per inch, which is the coarse thread. If your boss asks you for 10-32, that means there's 32 threads per inch, which is tighter than the coarse thread. There's more threads, they're tighter together, and that's the fine thread. There's no extra fine thread for this diameter. Okay, let's take a look at ½ inch. Very common bolt that you'll see in a machine shop is 1/2-13 coarse thread. If you want a finer thread, like inside of an engine bolt, or maybe wheel studs, then you'll go with fine thread, ½ inch-20. A common stud in a Chevy will have a 7/16 wheel thread, 7/16-20 fine thread. Again, you're dealing with high RPMs. So you go with fine thread, 20 threads per inch, versus the coarse thread, which is 14 per inch. Okay, so let's take a look at this one, number 10. So if your boss asks you for a number 10-32, how would you call this out on a drawing? So if your boss asks you to order a number 10 fine thread, then you will go to your previous slide, look at the table, look for fine, and it would tell you for fine thread, you're going to use 32 threads per inch. Okay, so you would call it out, the thread, the external thread is a 10-32, meaning 32 threads per inch if this has a length of 1 inch. If it had 2 inches in length, multiply times 32 and you would have 64 threads. So again, you always call it out as how many threads per inch. And the UNF stands for United National Fine Thread. And the number 10 doesn't stand for a 10-inch diameter. It stands for 0.190 as shown on the table. Now, out in the real world, you'll probably never have to calculate a minor diameter unless you're making your own threaded shaft. I've only had to create a customized threaded shaft. We had to use a large diameter shaft. I think it was about close to 2 inches in diameter. And we had to custom make this part, so we did have to do our own calculations using the ANSI or ASME standard. Okay, so for your homework, you're going to be using this formula. Okay, so just for practice on how to call out threads, we're going to be calculating minor diameter. Again, chances are you'll never have to do this out in the real world, but this is a good practice on how to look up threads on the table. Okay, so if you want to calculate the minor diameter, you'll take the major diameter, so the large D is for major diameter. Okay, so we know the major diameter is 0.19 for a number 10. Look it up on the table, 0.19. And you would subtract 1.0825 times P. That's the pitch. So the pitch is the inverse of 32. There's 32 threads per inch. So how far apart are the threads? That's the pitch. It's just the inverse, 1 divided by 32. So you multiply it times 1 over 32, or simply just divide by 32. So 1.0825 divided by the number of threads per inch. And that would give us a minor diameter of 0.156. So once again, our major diameter from our table, look up at number 10 on the table. Our major diameter is 0.190 minus 1.0825 divided by the number of threads. There are 32 threads per inch under the United National Fine Thread column. So first take the 1.0825 divided by 32, subtract it from 0.190, and we end up with a minor diameter of 1.56. So the major diameter is 0.19. The minor diameter from root to root, we get 0.156 diameter. And this is what you're going to be doing for your homework assignment. Okay, so what is the pitch diameter? I did mention it earlier when we discussed terms. And again, this is not something you need to know. It's not that important. But once again, the pitch diameter is where you have the length here cutting through the tooth is equal to this length in space. So that line to this imaginary line is the pitch diameter. Now for your homework, we're only going to deal with inches. In the next chapter, we are going to work with calling out metric threads. So let's go over metric. Okay, so to distinguish from inches, threads in inches, we're going to use the letter M for metric. So M stands for metric form, and we are going to be dealing with millimeters. So 6 tells us the major diameter. So major diameter is 6 millimeters. And instead of a dash number like in inches, the dash number tells us the number of threads per inch. Here the 1 doesn't tell us the number of threads per millimeter. It's actually telling us the distance from thread to thread. It's 1 millimeter, also referred to as the pitch. And most drafters and engineers, when they look at this, they will not know what they're looking at. This is something that you can look up in the back of your textbook in the index, and this will give us the class and tolerance to be used on the threads. So again, this is something you look up in the back of the textbook. And once again, we have to call out whether it's right-handed or left-handed threads. Okay, so here's an example of calling out a metric thread. Again, it's in millimeters, so M is for metric form. 6, so the diameter here is 6 millimeters. And the threads are 1 millimeter apart, and that's referred to as the pitch. And again, the 4G and 6G tells us the class of tolerance, how tight the tolerance is, and the tolerance on the diameters, and the crest and major diameter. So these are the tolerances. You can look this up on the table in the back of your textbook. Okay, so let's practice calling out a metric thread. Okay, so once again, the M tells us that we're dealing with metric form and not inches. And the 10 tells us we're dealing with a 10 millimeter major diameter by 1.5. 1.5 is the distance between the threads, also referred to as the pitch. And again, the 4H and 6H will indicate the tolerance being used. So for the pitch diameter tolerance, we have to look up 4H on the table in the back of your textbook. Same thing with the 6H for the crest tolerance and major diameter. And internal or external thread. And finally, if we're dealing with right-handed or left-handed threads. Okay, so this is a table that you'll find in the back of your textbook. So find this page in the index area. Okay, so again, this is the table for metric form, and we're using millimeters. Let's take a look at M16 by 2. Okay, so M tells us metric form. 16 is the diameter, so major diameter is 16 millimeters. And by 2 tells us the pitch. That's the distance between the threads for coarse thread. So general purpose thread. And for the tap drill, to drill that hole, we would use a 14 diameter millimeter tap drill. Now for fine thread, so now we're looking at the fine thread versus coarse thread. Coarse was M16 by 2. Fine thread is M16 by 1.5. The pitch is 1.5, telling us the threads are 1.5 millimeters apart. And for this type of thread, we would use a tap drill of 14.5 millimeters. And quickly, just to review from the previous slide, we were looking at a 16 millimeter diameter thread. The pitch for coarse is 2, for fine is 1.5. So as you can see here, the threads are tighter together than the coarse thread. And the tap drill sizes for coarse thread, we would go with 14, and for fine thread, we would go with 14.5 tap drill diameter. And for our minor diameter, using this formula, we would come up with 13.6 for the minor diameter. And that's for coarse thread, and for minor, we would come up with 14.2. Again, using this formula for the minor diameter using millimeters. And here's an example of calling out a metric thread, 16 millimeters in diameter, coarse thread. How would you call it out? Call it out as M16 by 2. So again, M is for metric form, and we'll know 16 is for 60 millimeter diameter. And the coarse thread, we go with 2, meaning the threads are 2 millimeters apart, and this is also referred to as the pitch. If it was fine thread, closer together, then we would use 1.5. Okay, in this example, we are attaching this plate to this one. So notice they have a different hatching pattern. So this hatching pattern is the same as this one, and it should be because this is one plate. And then we have a different pattern for the lower part. So this is a separate, let's say, block of aluminum. And this, let's call this one also aluminum. And we're bolting them down together or clamping them together. So the hole on the bottom block is tapped, so it's got the threads. And the hole in the first plate is just a simple plain hole, no threads. Notice how the hole is slightly larger than the bolt diameter. And this is referred to as a clearance hole, something we learned in a previous chapter. Again, Clearance holes are very common. That's just to provide room for a bolt to go through, and then it engages in the tapped hole. So you should be able to stick a credit card between the bolt and this clearance hole. So this is a smooth, plain, simple hole with a clearance of about 30 thousandths, which is about the thickness of a credit card. Okay, so for that clearance hole we were just talking about for the bolt, the clearance hole in the top plate, how much clearance should you use? So if we're looking at a 1-inch diameter bolt, you want to take the 1 inch and add 3/32, make a 1 and 3/32 diameter clearance hole. So that hole will be larger than the diameter of the bolt. If we're dealing with the 1/2 inch diameter bolt up to a 7/8, we're going to go with 1/16. So 1/2 inch diameter bolt, go with the 1/2 inch diameter bolt, the clearance hole, just add 1/16. So that'll give us 9/16. So it's just 8/16, which equals 1/2, plus 1/16 will give us a 9/16 clearance hole. And if you're dealing with smaller diameter, we're going to go with the 1/32. So 1/32 is about the thickness of a credit card. Okay, so take whatever diameter you're using from this range, and your clearance hole will be that diameter of the bolt plus 1/32, which is about plus or minus 30 thousandths, 0.03125 to be exact, and that's about the thickness of a credit card. And for metric, we use this table. So if we're dealing with an M6 bolt, meaning the bolt has a major diameter of 6 millimeters, we're going to go with a 6.6 millimeter clearance hole, as shown in the previous slide. If we're going with an M10, major diameter of 10 millimeters on the threaded bolt, then we're going to use a 10 plus 1, 11 diameter clearance hole, as shown on the previous slide, and so on. Okay, so these are tables for clearance holes, guaranteeing that the hole will always be larger than the fastener, in this case the bolt. So let's take a look at your assignment and go over at least the first problem. Okay, class, we're going to go over problem 15-1. We'll go over just the first problem and also the second one. Okay, so on your handout, so this is just a partial view of problem 15-1 handout. This is straight from the back of chapter 15 in your textbook. And there are 7 parts to it, A through G. We'll just go over A and B. All right, so let's go ahead and read the instructions. Write the thread notes for the following external threads. Okay, so this is going to be a bolt or a threaded rod, not a hole, not a hex nut, but an external thread on a shaft. So that's where we get the letter A. Okay, so for this handout, problem 15-1, we're going to have A for all of them, indicating external thread, so thread on a shaft. Also, what are the minor diameter and the pitch? So the pitch is the distance between the threads. And we're going to be using a thread class 2. So we have class 1, 2, and 3. 3 being the best, higher quality, tighter tolerance. But for this handout, we're going to go with the class 2 with good enough tolerances. Not as tight, and it should be cheaper to purchase a class 2 thread versus a 3. All right, so that's where the 2 comes from. So that's the class of thread, the quality, and the tight tolerance. All right, so let's take a look at problem A. Okay, so we're going to go over problem A. So we have a major diameter of 1/4. So let's take a look at the table on the right. So this table on the right, you'll find it in the back of your textbook. All right, so we're going to look down to 1/4. Okay, so here's 1/4. So anything that is a 1/4 and higher will be using a whole number or fraction. Anything below it will be using a hashtag number. There is a formula for calculating the major diameter when you use a hashtag number, don't remember exactly the formula. A machinist would know this. It's something like 12 divided by 64 plus 1/32 of an inch. This would be a number 10 would be a 10 divided by 64 plus 1/32. The formula is not correct what I'm saying, but it's something like that. I just don't remember it off the top of my head. All right, so we're going to look at a quarter. So let's take a look at that one. Okay, so let's take a look at a quarter. And the second column will give us the major diameter of the thread. The third column will give us the tap drill size, and it'll tell us the coarse thread. These are the number of threads per length of 1 inch. And we have fine thread. Okay, so we have UNF for United National Fine Thread, and we have UNC for United National Coarse Thread. Okay, and here's the column for the number of threads per inch for fine thread. So fine thread, the threads are tighter together. So when you're dealing with the bolt, that's going to go through a lot of stress, especially a bolt that's going to be attached to a moving part, like the internal parts of an engine, good example, or your wheel. So if you ever have to replace the rim on your car, the studs where the wheel mounts on, they use fine thread. So in that case, where you're dealing with the bolt that's going to feel a lot of stress, you're better off using more threads than less threads, like coarse. Coarse thread you tend to want to use on non-moving parts or bolts that don't go through a lot of stress as the fine thread. And then you also have extra fine thread. So United National Extra Fine Thread, UNEF. So for this, you typically see this on a aircraft. So to reduce the weight of an aircraft, which is very important for fuel efficiency, you know, an aircraft has thousands, tens of thousands of bolts and nuts. So one way to decrease the weight of an aircraft is to keep the bolts short, but then you're going to have less thread engagement. So we go with extra fine. So the threads here are a lot tighter. Okay, so we need enough thread engagement for the bolt and the nut to be effective, to do their job. All right, so let's go back to problem A. So we're going to deal with a quarter diameter bolt, quarter diameter. Okay, so now let's take a look at the type of thread. We're going to go with fine thread. So we're going to skip over to the fourth column, fine thread, and we're going to look down, and we can see there that for a quarter fine thread, we have 28 threads per inch. Okay, so the length of the bolt, if it's 1 inch, it has 28 threads. If the length of the bolt is 2 inches, then we'll have double 28 times 2, right? That's 56 threads over a length of 2 inches. Okay, so to calculate the pitch is pretty straightforward. Okay, so pitch, it's the distance between the threads. So all we have to do is take the number of threads per inch, which is 28, and take the inverse. It's just 1 divided by 28. Okay, so if you were to do the math, so problem A, the pitch equals the inverse of 28, so it's just 1 divided by 28, and that equals 0.357. Pretty straightforward, right? So very simple math. Okay, now we're going to write the note. So I completely forgot about the note. How do we call out a quarter thread, fine thread? Okay, so we have quarter. Okay, so let's take a look at the thread note. So we know we're dealing with the quarter major diameter bolt. Okay, so there it is. The dash 28 tells us the number of threads, right? So we know there are 28 threads per inch. And the UNF tells us that we're using United National Fine Thread standards. And the dash 2A tells us 2, it's an external thread. And A tells us that, my mistake, we're using A, letting us know it's external thread. And 2 is for the class. Okay, so that's the type of tolerance that they're going to use to manufacture this bolt, in this case. All right, so now let's calculate the minor diameter. So for the minor diameter, we're going to use this formula. Minor diameter equals major diameter minus 1.0825, that's our constant, times the pitch. Okay, so how do we calculate the minor diameter for problem A? All right, so let's do some math. Okay, so little diameter equals the major diameter. So here's the major diameter. Okay, so major diameter is 0.25. So all we have to do is go over here to the chart to the right. Major diameter is 0.2500. So we're going to go ahead and write that in. 0.25 is our major diameter. And we're going to subtract 1.0825. And we're going to multiply it times our pitch. Okay, so the pitch we already know is 1/28 or 0.0357. Either one will work. Okay, and that's our numbers for the formula. Okay, so all we have to do is do the math. Okay, so don't forget order of operations. So you're going to take 1.0825, multiply it times 1/28 or 0.0357, and whatever number you get there, you're going to subtract it from 0.25. Okay, so order of operations, you got to take 1.0825, multiply it times 1/28, or multiply it times 0.0357. Whatever you get, you're going to subtract it now from 0.25, and we end up with 0.211. Okay, so, and you can round off. I'll let you decide a number of decimal places to round off to. So that's how we come up with 0.211. Okay, if you want to go with 4 decimal places, 5 decimal places, 2 decimal places, I'm okay with it. Okay, so that's how you do the first problem, problem A. Okay, let's go on to the next one. So I'll go a little bit faster on the next problem. All right, so B, problem B, we have 7/8 major diameter. So we look down the chart, look for 7/8. Okay, so 7/8, and we're going to be using coarse thread. Okay, so we're going to go to the third column for coarse thread. So 7/8 has 9 threads per inch. Okay, so 9 threads. Okay, so to calculate the pitch, we take the inverse of 9. So the pitch equals 1 divided by 9, and that equals 0.111111. Goes on forever, right? Okay, so you can round off or use the number of decimal places you want, 2 decimal, 3 decimal, 4 decimal places. I'll leave it up to you. Okay, so now let's go ahead and calculate, or I should say write down the thread note. Okay, so the thread note. Okay, so we're dealing once again with 7/8. So we go 7/8 dash 9. So it's not minus, it's dash. Dash 9 tells us that there are 9 threads, right, per inch. 9 threads, coarse thread, 9 threads for a 7/8 major diameter bolt. Okay, so that's how we come up with the dash 9, and UNC stands for United National Coarse Thread, and the dash 2A, okay, so the 2 tells us we have a thread class of 2, and the 8 tells us we have external threads, right? Okay, so threads on a shaft. All right, so to calculate the minor diameter, okay, so for the minor diameter, we're going to once again use our formula. Okay, so minor diameter equals major diameter. So major diameter is 7/8 or 0.875. If you do the math, 7 divided by 8 is 0.875. Okay, and then we're going to go minus 1.0825 times the pitch. Okay, so to calculate that, I'm going to do it over here to the right. I don't have enough room here, so okay, so we're going to go with minor diameter equals 7/8. Okay, so 7/8 or 0.875, right? So minus 1.0825 times 1/9, right? Or 0.111111. Okay, so once again, 0.875. But we need to respect order of operations, so we need to first go 1.0825 times 1/9, or 0.111111, right? So whatever you get, you're going to subtract it from 0.875, and that'll give us 0.755 for the minor diameter. Okay, so that is 0.755. You can round off if you like. I'll leave that up to you. Okay, so that's how you do the second problem. Okay, and just do the same thing for the rest of the handout. So it's a total of 7 problems, and that will be provided for you on through Canvas and also through email. Not only the lecture notes, this lecture note, or I should say this chapter 15 lecture notes, also a handout for the assignment and a handout for this table that you see on the bottom right corner, which is in the back of your textbook. All right, end of lecture.